Alright guys, Dr. Wheeler here. Today we're going to be taking a look inside of this Harbor Freight Oscillating Multitool. So what this thing is it's got a tool attachment down here. You can get varieties of different sorts of tools, saws. I've got a smooth cutting blade on here right now. When you turn this on, this blade jiggles back and forth like so. Show that off. There you go. And what you can do with that is you can use this for scraping things off. You can put a sanding head on there and sand material with it. You could put a saw blade on and cut things off. And it's a handy tool for getting into tight spaces and cutting and sanding different things. So let's take a look at how this thing is put together. Before we go inside, I just want to point out a few features on the outside of here. So first of all, we can flip this over and we can take a look at some of the labels that are present on this tool right here. So first of all, this tells us what kind of power this runs off of. So you see down here, we're running off 120 volts AC, so a wall plug, 60 hertz, that's the North American AC frequency, and we're told that this is going to draw a max of 2 amps. So from that, you should be able to figure out what the max power of this tool is. We'll also notice up here we actually have a regulatory marking also. So that says ETL Intertech, and then there's a number here which I'll read off to you. It is 4006248, right? And this is going to tell us what sort of testing this has been subjected to make sure that this is a safe device for you to use. All right, and we can look more broadly at the outside of this tool. We can see it's actually made out of a variety of different materials here also. So there's some sort of metal casting or a metal injection molded part up here at the front. It looks like it's got some paint over the top of it also. So it'll be interesting to see how this is made when we take this apart. We also notice that a lot of the tool is made out of plastic. Most of the housing is plastic, but it's not all the same sort of plastic here. So this red part is hard and rigid and seems to be giving the handle most of its strength. But then over top of it, there's this black rubbery stuff that's to make it, give you a nice tight grip on this, because it does vibrate quite a lot when you're using this tool. You can see some of this black stuff, which we typically call the overmolding, is starting to peel off a little bit here also. So when we take this housing apart, we'll take a look at how that's made also. And then down here on this end, we've got our standard wall plug that gives power to this device. So it is taking the wall current in, and there is down here a dial that I can set to different values. It goes from 1 to 6, and that allows me to set the speed of this. So that's the max speed there. So I can adjust that, and it appears to be that this is infinitely variable, so I can control the speed. It's not just 6 different speed settings. I can change it to be whatever I want it to be. All right, so a few things that we'll be looking at in here is how does this thing work? So we can kind of guess that there's an electric motor that must be spinning in here. We want to look at how do we translate the rotary motion to this back and forth oscillating motion of the cutting blade, and how are we doing speed control, right? So we're somehow taking power from the wall, we're converting it somehow. There's some sort of electrical circuitry in here that will send the power to the motor, but also set the speed of the tool. So we'll try and figure out how that works also. And let's go ahead. I'll unplug this. Always a good thing to unplug it before we start taking this apart and exposing ourselves to the wiring. And we'll take a look inside and see what's going on here. Okay, we've got 3 of these long fasteners that held the clamshell of this tool together. So with those removed, I can just slide this piece off. We'll take a look inside of there in just a minute. But we're exposing most of the circuitry of the tool here. So we can see we've got our dial that sets the speed. So we'll pull this board out and take a look at what's going on in there. We can also see a connector here that's connecting to the electrical switch that turns the motor on and off. So the switch to turn the tool on is up here, and if you move that back and forth, you see it's connected via this plastic arm down to the actual switch, which is down in here. We'll take a closer look at that in just a second also. There's also some sort of electronics housing down here that we'll pull out and take a look at, and we can see that there's power going to the motor over here. So underneath, this is not factory electrical tape, I don't think. We've had this tool apart several times from students. You can see the beginnings of the motor here also. So we've got an electrical connection that comes down here to part of the electric motor. So let's continue taking this a bit further apart, and we'll take a peek at what we find in there. All right, let's take a look at how the tool itself is retained onto the power tool. So this cutting blade up here, you can change these out, and there's a screw with a hex socket in there that you can tighten and loosen to change the tool out. And you'll notice there's also a washer under here, and if you look from the side, it is not simply a flat washer. So this is actually kind of cupped, sort of like that, and when you tighten down the screw, it clamps against the surface right there. That is called a Belleville spring washer. You can look that up, and one of the questions on your homework is why are we using this sort of spring washer in this application rather than just a flat washer? All right, so before we go much farther here, let's take a look inside of the housing. We can see we've got some markings here. So there's one marking up here that says TPE. There's some sort of part number listed right here. We have a recycling mark of a number 7 here. And we have another marking that says PA6GF30 down here. So the TPE and the PA6GF30 are different material indicators telling us what this housing is made out of. TPE will stand for thermoplastic elastomer. That's going to be this rubbery stuff on the outside, the grippy stuff. And then PA6GF30, PA6 stands for polyamide 6, probably better known as nylon 6, which is a specific type of nylon resin. And the GF30 means that this particular nylon is been glass filled, so it's got fiberglass. The GF be glass fiber, 30%. So this is going to be about 30% glass fiber. That makes the nylon a lot stiffer and improves its material properties. So you notice if I squeeze this, it's got some play to it, but it's a fairly stiff part here. If this was just pure nylon, it would be too floppy to really use as a tool housing. There's also some interesting features inside of here. So you notice there's things like these ridges which help stiffen the tool housing. There's also some places for the fasteners that's holding the clamshell together. But there's also some features in here that don't appear to have any bearing on the stiffness of the housing. Things like these nubs over here. And if you look up the overmolding process that you use to make this grippy stuff on the outside, I think you'll find that those will be locator marks that make sure that the part is properly located in the mold that's used to apply this overmolding compound. Because you notice here, see the overmolding is actually dovetailed into the housing here. It's not just glued onto the surface. This is actually injection molded around the nylon part, so that it's basically one piece here. You can see right where they put the TPE compound through this hole in the mold right here, that was probably the injection point. So the TPE flowed through that hole and then around the housing to form this. You can see where there's a bit of mold flashing here on the inside of the tool where it's, the TPE sort of leaked beyond where it really needs to go. But over on the outside of this, it looks pretty good. Sometimes on Harbor Freight tools, especially the really low end ones, you can see where this TPE won't quite line up where it was supposed to be. It'll be slightly off. and that was because the nylon part was not properly located inside of the mold when the TPE was applied to the part, so the TPE is a little bit misaligned. This one's pretty good. The Chicago Electric brand is it's one of Harbor Freight's kind of middle of the road in-store brands. On some of the Drill Master ones, you'd be more likely to find that because those are really the really inexpensive, low-cost tools, and the quality control on those is not quite as good as they are on the Chicago Electric. So one thing to keep in mind if you're thinking about the end of life of this product, even if we're just looking at this one piece here, which we have manually separated, we've pulled out all the metal, this is just plastic. How do you recycle something like this, right? As it's got two completely different plastics connected together, they're not even glued together. It'd be really hard to peel this TPE off and separate that so that you could get the two resins separately. So that's some food for thought as you reflect on what it would be like to recycle this product at its end of life. Alright guys, so I took apart the tool a little bit further and got the electronics board out. It was retained, so it was mounted up here like that. And it was retained with this other injection molded part, which also says PA6GF30 on it. So this is also the nylon with the glass fiber fill. But you'll notice in this part, it is just left a white color, whereas in the tool housing, they dyed that red to make it the correct color for their brand of tool, where here they saved a little bit of cost by not adding any dye to the plastic. So once you pull that off, you can get to this control box here, which has a potentiometer connected to it so that we can, and this is the actual speed control. We can see 3 wires going from the potentiometer down into the electronics here. There are some markings on the other side. I've tried looking them up, and they don't return any hits on Google, so it's some sort of proprietary part number where we can't find a data sheet. So it's hard to tell what's going on inside of this part because they've taken epoxy, so they've had a circuit board down inside of this outer plastic box, and then there's epoxy poured over all the electronics, which is actually a good thing for the longevity of the part here. What that does is it helps minimize vibrations, so none of the parts can wiggle against the circuit board and fatigue the leads on the components and have those break off. So that should prevent that from happening. It also prevents any water or anything else getting into the electronics. So overall, a good thing for the tool's longevity, but it does make it very difficult to tell what's going on in here. Then we can see that there's a couple of components poking out above the epoxy here. So first of all, there's a component with a large heat sink here. If we were down in CTLM 123 and we pulled a component out that looked like this, we would guess that it would be a big power transistor or a MOSFET. Since this does run off of alternating current, there are some other components it could be. It could be what's also known as a triac, which is another type of semiconductor switching device that gets used for speed control also. And you can look up a triac speed control circuit and you'll see that there is one that's very similar to this that is controlled by a potentiometer, and that is a strong possibility for the way that they're controlling this universal motor. I did try and hook this up to the oscilloscope and see if I could get a waveform to see how they were controlling the motor. Unfortunately, I just can't get the tool to run well enough while I've got the oscilloscope hooked onto the brushes to get a clear enough waveform to get an idea of what's going on. But that's one guess here. So we do have this potentiometer coming down. There is another second little potentiometer that appears to be set at the factory. So there's a little screw hole right here where I could go in and adjust the circuit. So they could be tuning like a voltage divider or setting some parameter at the factory using that. And then there's a couple of capacitors here also, which could just be for doing some filtering. But that speed control circuit that uses a triac does have a large capacitor in that circuit, so that could be what we're seeing here also. Again, can't tell for certain because we can't take this all the way apart. Maybe if we got some solvent or something and dissolved all of this material away, we could figure out what's going on inside of there. But for now, we're just going to have to treat that as a black box to figure out how this is working. All right, so, but basically, we can see that there is power that comes from the line. Let's see, down here. So we can see the black wire here is going to be our hot side of our power. So that's like the positive side on a DC circuit, but that's where the 120 volts AC is coming through. It goes through the switch into this blue wire, which goes down into the board. There's a second blue wire that goes out and is soldered here into a white wire, which then goes up into the appears into the field windings of the motor, and it must connect to the brushes somehow also underneath this housing that we can't get apart. All right, so that is the basics of what's going on with the electronic circuits in here. So let's keep going on and we'll take a look at the motor. All right, so I've removed some of the fasteners from up here on the front of this metal casting up here that was holding it to the housing of the tool. And once I've done that, I should be able, there we go, just pull this thing apart. We've got a little extra plastic piece that keeps dust from going back down into the body of the tool here. Right, but let's take a look at this front half. You can see we've pulled out part of the motor here, right? And there's quite a lot going on this tool here. So we've got a central shaft, and this would be the rotor of our motor because it is the part that spins, right? And we can see we've got multiple windings inside of here, right? So on the rotor we have lots of different windings, and then they're all connected down here to this part here we call the commutator. So the commutator is going to be spinning along, and you notice it's got these little copper pads that have divisions between them. So what the commutator does is it makes and breaks connections going to these different windings that go through the rotor of the motor. And then on the tool housing over here, the electrical contact that's actually delivering power to the rotor, right? So the commutator is where the power goes into the different windings to make the motor actually run. It goes through these brushes here. So this is the back of the brush. If I pull that out, whoop, it's gonna fall apart on me. But what the brush is it is a piece of graphite that makes contact. They've fallen down inside of the tool here. Here's one. There we are. All right. They're pieces of graphite that rub against the commutator to make electrical contact. This one has gotten a bit broken from being taken apart several times. They're normally a little more square, so these are going to continuously push against the commutator. They have a spring behind them that forces them in because they will actually wear out over time, right? So the graphite's very soft and it's rubbing against the commutator continuously as the motor is spinning. This will gradually wear out. Now, on a lot of tools that use a brushed motor like this, there'll be a slot in the housing. A lot of times you'll see it here where it's like a little screw-in housing above the brush where you can take that out and you can put a new brush in when the brushes wear out. Because this is such an inexpensive tool, Harbor Freight has decided not to include that feature because they don't really expect you to replace the brushes when the tool wears out. They expect you to just throw it away and go buy another tool from Harbor Freight. So that is an interesting place where they've saved some costs on that. So that is a look at the rotor inside of our electric motor. This particular type of electric motor I want you to look up is called a universal motor. It's called universal because it will run off of either DC or AC current. It doesn't matter which way, which type of power you supply to it, this will spin and it'll run okay. So with alternating current, the trick is your current keeps changing directions. So if we just had a simple basic brushed DC motor design, and we tried to supply AC power to that, the electric field would keep changing directions and you wouldn't get a torque going in one direction to get this to spin continuously. Hence we have all these different windings on the rotor and the commutator, which allows us to keep switching the winding that's energized so that we could get a continuous torque in one direction and we get this to spin consistently in one direction. Now, to give this a magnetic field in which to spin, there's also the field windings inside of the tool housing. So we can see we've got two big bundles of copper wire here that are going to produce a magnetic field for our rotor to spin in also, right? So that's how this whole motor works together. So we should be able to pull the field windings out. We've got a couple of fasteners here. You can see they're starting to get kind of stripped out from being taken apart a few times. This tool is really not designed to be taken apart, especially not as many times as we've taken it apart for this class. So you can see, again, that's just one of the features where this wasn't really designed to ever be repaired. Let's take apart this, pull the field windings out, and we'll take a closer look at them also. All right, so I pulled those fasteners out of the field winding and started pulling on the field windings, and they don't want to come out. They are really in there, and I've also noticed that back here where we make our electrical connection to the field windings, you can see this wire that's coming in to this metal housing right there, and then it is riveted onto the field winding housing here, so you cannot pull this out the front anymore. That is in there, and it's not going to come out. It is interesting to look down here also. You can see another part of the motor way down at the bottom down here. There's a little ball bearing for the rotor shaft. That's where this shaft ends up, and that's how we support the rotor so that it's supported on both ends of itself, so that we can have that spin at very high speeds. Now when I have the rotor separate from the tool, I can spin that manually, and you can see how it's translating that motion into the back and forth motion of the blade there. Right. So we should be able to take a peek inside of this housing here and figure out how that's working. I'm just going to pull on this. It's starting to come. There it goes. All right. And we can find the mechanism that makes this, turns this rotational motion of the motor into the back and forth oscillating motion of the blade. You can see inside of there's sort of this fork that's directly connected to the blade, and then inside of that fork we have this cam that's going to fit in there. That's smooth, and oh, this is actually a bearing. This spins freely, but if I spin it in the housing, you can see it's actually off center. There it goes. So you can see as I spin that, we get that off-center eccentric motion, and this bearing is going to be fitted inside of the fork, so as that spins, it's going to push the fork side to side, which is how we get the oscillating motion of this tool. All right. Another interesting thing to note about this, there is a ton of grease inside that housing right there. Okay. So this is definitely a well lubricated tool coming straight from the factory there. There's just grease all over the place inside of there to keep all these parts where we have metal to metal contact, to try and keep those to last as long as possible, right? But that's actually quite a simple mechanism in there. It's just a direct drive, so you can see there's no gear reduction or anything. There's no gearbox in this. However fast the motor is spinning will be however fast this is oscillating. So if we have this tool set to its max setting, or it's saying that it's going at 21,000 cycles per second, so it goes back and forth 21,000 times per minute, per minute, then that means that this motor's got to be spinning at 21,000 RPMs also. So this little rotor is going to be spinning quite fast inside of the tool. All right, I just want to point out a couple more features here on the rotor of our universal motor. One is these marks in the side of the rotor. You see they're spaced out periodically on the rotor, and these are definitely intentionally done here. So one of your questions for your assignment is, why are these marks in the rotor? A hint for that, think about how fast this thing is spinning and what would happen if these were, the rotor wasn't perfectly balanced. So think about that in your answer there. Also, we've got this white plastic piece. Again, it appears to be made out of nylon. It has these fins on it. We're going to ask you, what is this part here and why is that there? Another interesting thing here on this machine part here that fits in, we have a rubber O-ring here to seal up the housing here with the mechanism and keep all the grease from ending up into our motor, and also I think to keep dust and little bits of things that we're cutting from getting into the mechanism here that causes the tool to oscillate back and forth. I also think it's quite interesting that the eccentric part right here is actually a bearing, so this can spin independently from the rotor itself. So if you go back and look at where I turn the multi-tool on, you notice for a couple of seconds the blade goes slowly back and forth, and then it gradually speeds up until it gets up to full speed. That would be why right there. So it's sort of a soft starting feature where the blade isn't going to oscillate back and forth at full speed until it has a little bit of time to get up to speed. There's also another bearing inside of here. There, you can see this can spin freely and independently. So there's a ball bearing at both ends of this shaft. Right. Another question on your homework: why do we have two bearings on this shaft?